All right, hey y'all, it's Miss Summers with some notes today on Kepler's laws. All right, so what we want to learn today, or what we're going to talk about today, is Kepler's laws. There are three of them. They have to do with planetary motion. All right, you need to be able to describe each of them and what they all imply. Okay, so throughout these notes, I have the PowerPoint, obviously. I will be kind of jumping between screens between this, and then I have a camera that's on me because I want to show you some examples, ways you can look at things, and the best way to do that is in person. So, have something to write with, something to write on. Throughout this PowerPoint, you'll notice some of the font is in white and then some is in yellow. The really important stuff is in yellow. That's what I want you to focus on, okay? The stuff in white is kind of, it's there, I'll talk about it, but I need you to know the stuff in yellow, so hint, hint, wink, wink. Okay, so let's go ahead and start. You'll note all of this is in white, which means you don't necessarily need to write this down. But I want to introduce you to this winner right here. His name is Johannes Kepler. He was born a long time ago. He was born in the 16th century, worked through the late 16th century, early 17th century. He's from Austria. Again, I don't care if you know that. But he was interested in how planets move. So you got to remember, this is back in the late 1500s. This is like right after the time of Galileo and Copernicus. You know, we realize that the solar system is not geocentric, or the universe is not geocentric, that things don't go around the Earth, things go around the sun. Okay, to the best of their knowledge, things went around the sun. So he wanted to know how planets did that. And he went to his teacher. His teacher's name was Tycho Brahe. Brahe had this really, really, really great little island, I think off the coast of Denmark. And he had a planetarium there, or an observatory, I should say, not a planetarium. But he had an observatory. He could watch where the known planets were, and he got these crazy accurate measurements. But Brahe didn't know what to do with the numbers. He had these good numbers, but Kepler is the guy that saw the pattern in them. Okay? A little background. All right. Oh, looky here. This is in yellow. That means you probably want to know that. So at the time that Kepler was working, most people thought that planets orbited the sun in a circle. All right, circles are very natural shapes. It's actually a really easy shape. It doesn't take a lot of energy, so a circle just seemed like a good fit. Okay, but Kepler realized with all the planets, but especially Mars, he was able to prove his point really well. He said, nah, they don't go in a circle, they go in an ellipse. Now, what an ellipse is this. It's basically an oval. All right? So that led Kepler to his first law. So this is the first law. Excuse me. A planet's orbit is an ellipse with the sun at one focus and nothing at the other focus. All right? So what a focus is, the plural is called foci. Okay? A focus is sort of in the middle of the ellipse if you cut it long this way. Hot dog style, I guess. Yeah. All right. It's in the middle this way, and then they are symmetrically distant from one another if you cut the ellipse in half this way. All right. So here's the sun. This is nothing here. This is just an empty point in space. All right. So he's like, that's really cool. This is also called the law of ellipses. So a planet's orbit is an ellipse. All right? Which means because planets don't go in circles, they go in an ellipse, that means there's different parts in our orbit. We end up with these 2 points called perihelion and aphelion. And I want you to take a minute, you can pause the video, I want you to see if you can figure out what that difference is, looking at this diagram. All right, now we're back. So here's the difference that hopefully you observed. Perihelion over here is when the planet is closest to the sun, okay? So this distance is the smallest distance between the planet and the sun. Aphelion is the opposite. Aphelion is when you're really far away. So you can think A is away. That's how I remember it. Okay? Now you will note I put this in here, and some of y'all are still gonna confuse this, and you know I'm gonna repeat it until you don't, until you learn. All right. Perihelion occurs every year around the first week of January. Now you might be like, that doesn't make sense because January is winter, and winter is when it's cold, Miss Summers. Very good, it is. But what I want you to see from this is distance from the sun does not change seasons. Distance from the sun does not change seasons. I'm going to say it one more time, which means you should write it down. Distance does not change seasons. Okay? Because if that were the case, it would be the same season everywhere on Earth if it was, because the whole Earth travels like together. It's not like one part of the Earth moves differently than the other. All right? Seasons are caused by tilt. And we're going to have a whole 2 days on that, so don't you worry if you're still not okay with that. We are closest to the sun in January. We are farthest from the sun usually the first week of July. Okay? So remember that A is away, aphelion is away, perihelion, you're close. All right? I want you to be able to describe an ellipse. When we describe an elliptical orbit, we have something called eccentricity. And I describe that as how stretched out an ellipse is. How ovally is it? Eccentricity is a number. It does not have a unit from 0 to 1. If you have an eccentricity of 0, it is a perfect circle. It is not stretched at all. If it is an eccentricity of 1, it is a straight line. It is nowhere near a circle. All right, and you can see down here in this diagram, the bigger this number gets, the more stretchy it becomes. So if we look at this diagram, we have 4 heavenly bodies. We have Pluto, Neptune, Jupiter, and Halley's Comet. Which one is most eccentric? It's definitely going to be Halley's Comet, because you can see that this is a stretchy oval. These other ones, Pluto, Neptune, and Jupiter, these are ovals. I know you might be like, Jupiter, that's a circle, Miss Summers. It's not. If you measured this distance and this distance, they'd be ever so slightly different. Maybe not a whole lot. This is a very low eccentricity at Jupiter, but it's still an ellipse. It's still an oval, because Kepler's first law says that planets orbit in ellipses, aka ovals. Okay? So, because you don't have to write this down, because planets orbit in elliptical shapes, they are not always the same distance from their stars, which in our case is the sun. And that leads us to Kepler's second law. All right, now before I jump into what Kepler's second law is, I want to show you a quick little, where's my thing? There I am, haha, there I am, hello. I want to just quickly show you a little diagram, a way you can think about Kepler's second law. It's with these 2 containers of liquid, okay? So I have this 100 milliliter beaker down here that's filled with blue water, and then I have this 100 milliliter graduated cylinder that is also full of blue water. If you were to give a very small child this test, they would fail it. Not because they're stupid, it's because they're small children. They can't help it. All right, if you ask a small child which container has more liquid, they would be like, the taller one does, because that's how their brains think, because it's how they perceive the world. Okay, but you are not a small child. You are like Miss Summers. You said both of these were 100 milliliters. Haha, I did. All right, which means they both have the same amount of liquid. This one is taller because it is skinnier, okay? So in order to accommodate 100 milliliters in a container that has a smaller diameter, all right, it's not as big around, it has to be taller. Likewise, this one, okay, it's not as tall, which means it has to have a wider diameter. It has to be short. We have a short, fat container, and we have a tall, skinny container. Keep that in mind. All right, I'm going to go back to the PowerPoint. Haha, it's right here. So Kepler's second law states that the line joining the planets to the sun sweeps out in equal areas in equal times. Okay. If you see a diagram like this, it's always Kepler's second law. If you see a diagram like that, just pick Kepler's second law. Just pick it, because it's right. Okay. So we have a tall, this isn't the best diagram in the universe, but we have a tall, skinny triangle here. It takes a planet 1 month to move this little itty-bitty distance. And then we have a short, wider triangle here. It takes a month to move a larger distance. So now, imagine this is the tall, skinny triangle. This is a short, fat triangle. They are the same area. This means that our speed is going to change, okay? This has to go a greater distance in the same time. This goes a smaller distance over the same time. The speed of something is equal to the distance over the time. So if you got to go farther, you got to go faster. Likewise, if you're farther away, or if you have a shorter distance here, this would be like a skinny triangle. It doesn't have to go very far. It's going to move slower. Write this down, put a big old star next to it. This is the biggest thing with Kepler's second law. Planets are going to move faster at perihelion when they are closest to the sun, and they are going to move slowest when they are farthest from the sun at aphelion. Okay, so again, we have our long, skinny triangle here, or right here, this would be a better example. You see how it doesn't have to go very far? It can go nice and slow. And then here, when it's closest, it has to make a short, fat triangle. It's got to go, it's got to go a lot faster, okay? An example where you might have seen this is a side tangent. If you've ever seen the movie Apollo 13, first off, it's a great film, Tom Hanks. But it's about the Apollo 13 mission. Basically, there were 3 guys. NASA sent them up. They were supposed to go to the moon, get some rocks or whatever. And halfway there, they had a catastrophic failure of one of the systems on board their little spaceship thingy. And the mission turned into, we have to get these people home. We have to get them back to Earth. They can't go to the moon anymore. And the problem was they had 2 options, essentially. They could either stop where they were and turn around and try to hobble back to Earth, but there was no way they could stop themselves. You can't really stop yourself in space. It's hard to do that. So what they ended up doing is they took advantage of Kepler's second law. What they said, they're like, hey, keep going towards the moon. When you get really close, go around it. That'll increase your speed and give you enough power to get back to Earth, which is what they did. It's part of what they did. And they did some other really cool sciencey stuff, and they ended up making it. Cool story, bro. Right? Science. Cool. Okay. Next, the third law of planetary motion. All right, I'm going to read this. Please don't write this. The ratio of the square of revolution time for 2 planets is equal to the ratio of the cubes of their semi-major axis. If you don't know what a semi-major axis is, or what a revolution time is, this doesn't make sense. So I want you to write this down instead. There's a relationship between the time it takes for the planet to go around the sun and the average distance from the sun. Okay? Again, like I said earlier in the year, I'm not going to make you do math. There is a mathematical equation that you could do with this. I'm not worried about that. Okay? But basically, the time to go around the sun once, which we call a year, the time for 1 year is proportionate or proportional to the distance. Which kind of makes sense. Oh, let's go to our next one. There we go. They have it graphed here. Square of orbital period, that is years squared. So how long your year is in Earth days squared. And then cube of the semi-major axis, that's the average distance cubed. Remember, it's an average because sometimes you're closer and sometimes you're farther away. All right, planets that are really close to the sun, okay, they have a very short semi-major axis, have very short years. Planets, as you get farther away, so again, here's the distance. If you get far away like Neptune or Pluto, you end up with really long years. Basically, if you're closer to the sun, you have a shorter year. And the opposite of that is true. If you are far away from the sun, it will take you a really long time to go around, which makes sense. Think of it like a racetrack. Like if you were like on the football track or whatever that goes around the football field, all right, and you had to stick in one lane, the inside lane, the one that's closest to the field, the middle, that one's shorter distance-wise. The one on the outside is longer. All right, so we have this nice little diagram here. You can see how long it is. Mercury is named after the Roman god Mercury, who was the Roman version of Hermes, which you might have seen in like cartoons or movies or whatever. He's the guy that wears the sandals with the wings on him because he's the messenger. He goes really fast. Mercury was named that because early astronomers realized, hey, Mercury moves really quickly. So that's why they named it that. All right. Pluto, poor Pluto out here, is not even a planet anymore. Aw. Pluto takes 90,000 Earth days to go around the sun once. It hasn't even since we discovered Pluto like 90 years ago, it hasn't been around the sun once. It takes like 200 some odd years. Crazy. All right. So that is helpful. Knowing Kepler's third law is helpful when we're looking at other planets, because if you know the distance of a planet, you can figure out how long the year is, and likewise, if you know how long the year is, you can figure out the distance. One of the big things with astronomy right now is finding planets that could harbor life. And the big requirement for a planet to have life is it has to be in what's called the Goldilocks zone, where it's not too hot and it's not too cold. It's at the right distance. So by watching as planets go around other stars, scientists can figure out, okay, it takes it this long to go around, which means it's probably this far away, and that's either way too close or it's way too far away, right? So that is Kepler's third law, that's Kepler's third law. Kepler's laws are really snazzy because they apply to any celestial body orbiting something else. So when we look at planets around a sun, or the moon around the Earth, okay, the moon orbits in an ellipse. Sometimes it's closer, sometimes it's farther away. A satellite, we want to know where satellites are, how they're going to move, because that affects how they work. All right, so that is why these laws are helpful. All right, so just to recap real quick before I let you go, we have 3 laws that Kepler discovered. Kepler's first law is the law of ellipses. Planets go in an ellipse. At perihelion, they're closer. At aphelion, they're further away. Kepler's second law is the law of equal areas. Planets sweep out in equal areas and equal times, which means that they have to move fastest at perihelion and slowest at aphelion. And Kepler's third law, the law, is called the law of harmonies, which is a pretty sounding law. Aww. Which basically states that the closer a planet is to the sun, on average, the shorter its year will be. Planets that are really far away from the sun will have longer years. Okay? So, you have some practice that I posted up for you. I will do some demonstrations and some other stuff tomorrow on Kepler. So, if you have questions, please let me know either in the comments or on Canvas or email or whatever, and I'll talk to y'all soon.